Hello, good morning to everybody. Today we'll start the last part of Physics 2, and this is the lecture number 11. We'll discuss about the optics. Actually, there are two types of optics. One is geometrical and another one is physical optics. So, physical optics, especially will concentrate on physical optics. And we will discuss some different important parts of optics, especially interference of light and Newton rings and diffraction of light, polarization of light, etc. First of all, we'll discuss on light with a historical background. Light is an electromagnetic wave. We must know about this. So first of all, what is the light? For centuries, the nature of light was disputed. In the 17th century, Sir Isaac Newton proposed the corpuscular theory. That means wave theory of light, stating that light is composed of particles. Other scientists like Robert Hooke and Christian Huygens believed that light to be a wave. Today we know that light behaves as both wave and as a particle. So light undergoes interference and diffraction as all wave do. But whenever light is emitted, it is always done so in discrete of packets called photon. Must know what is photon. These photon carry momentum but not mass. So this is the actually historical background of light. On the wave versus particle, light is an electromagnetic wave. As light travels through space, an electric field and a magnetic field is oscillate perpendicular to the wave direction and perpendicular to each other. We'll learn more about these fields in later units. A light wave is transverse rather than longitudinal. Since each field oscillates in a plane perpendicular to the direction of the wave, unlike a pulse traveling down a length of rope, nothing is physically moving in a light wave. Light requires no medium. It can travel through space that contains matter such as air, glass, water, etc., or through a vacuum. If light did not need a medium in order to propagate, the earth would spend its days submerged in darkness and the sun would not be visible. So it is actually very important part, that means wave versus particle of light. So you must know what is about the electromagnetic wave. Electromagnetic field affects charges. Light is an electric field coupled with magnetic field. You must know about it. The two fields oscillates together, but at different planes. To visualize an electromagnetic wave, you must think in three-dimensional geometry. Let's put a light wave together with one piece at time. Okay. So electromagnetic wave, this is the actually the wave like this, and XY coordinate, Z coordinate. This is the from YZ plane. Okay. So electromagnetic wave, uh, we can figure out like this. And frequency and wavelength, we must know frequency of a light wave corresponds to the color we see. The amplitude corresponds to brightness. Actually, light frequency of light give color, but sound pitch. Amplitudes for light brightness and sound will be loudness. So frequency, depending on frequency and wavelength, high frequency, we get small wavelength, low frequency, long wavelength, and vacuum speed of light in vacuum is constant. You must know about it. So there is gamma ray, X-ray, ultraviolet ray, infrared ray, and radio ray. Wavelength are different in different scale. So historical background, before Galileo's time, around 1600, many people believed that light was infinitely fast. It's so fast that it seemed like it to took no time to get from one place to another. Galileo and an assistant went to an Italian countryside a mile apart and tried to measure the speed of light by timing it. All they could determine was that light is much faster than sound. But later that century, around 1667, a Danish astronomer named Old Reaumur made the first accurate measurement of the speed of light. So after Galilei, he gave his theory on light. So historical background, you can write the Earth moving in 6 months later, and Earth now this. So Jupiter, 6 months is Jupiter now this. So because, and you must know, light of speed of light is constant in vacuum 3 into 10 to the power 8 meter per second. So after Riemann, Bernard Foucault also made the accurate measurement of the velocity of C, that means velocity of light, which is a constant in vacuum. So Michelson-Morley experiment, Albert Michelson is the best known for an experiment he did with Edward Morley in 1887. At the time, it was understood light needed to be medium through which to travel. It was proposed that light traveled through the visible ether in space. The Michelson-Morley experiment was an attempt to detect Earth's motion through the ether. There's how it worked. First, imagine you are standing still outside and there is a wind coming from the north. If you run north, you will measure a greater wind speed. If you run south, you will measure it slower, whether you run north or south, though you will still feel the wind coming from the north. If you run east or west, however, not only will the wind seems to change speeds, so it will its direction. Now imagine a race between two equally fast swimmers. They each go the same distance in a river, but one goes upstream and back, while the other goes directly across the river and back. With no current, the race would definitely be a tie, since their speed and distance are the same. With the current, however, the cross-stream swimmer will win. This is not obvious. You should try to prove this. For a hint, you can write. This is actually a real-life example of Michelson-Morley experiment. So Michelson built something called the interferometer to try to measure a change in the speed of light in two different directions. The Earth moving through the ether around the sun is analogous to a wind or current. Instead of racing to swimmers, Michelson raised beam of light. Light was shone into a mirror that allowed half of its pass through. Each beam traveled the same distance before the reflected back and allowed to recombine. Based on the interference pattern of the combined wave, Michelson should have been able to detect a winner. But no matter how the experiment was done, the race was always a tie. This eventually forced physicists to abandon the ether theory. Einstein resolved the problem in 1905 with the theory of special relativity. In its assert the speed of light is the same no matter how fast or the way an observer is moving. So light versus sound, we can discuss about this. Actually, sound, you must know, a bolt from the blue, and after blowing, we get the sound. So the speed of sound is less than the speed of light. So this is actually real life example of the light versus sound. So actually, light versus sound, you can calculate distance equal to velocity multiplied time, 258. Now, light waves and sound waves are different. So we can resolve the answer with a suitable example of it. So speed of light is a constant in vacuum. Actually, why objects have color? actually depending on different wavelength of light, which give in its a white appearance. When the light hits an object, certain wavelengths are reflected and they are absorbed. The reflected wavelengths are the ones we see and determine the color of an object. In the first picture, the tomato absorbs the blue and green wavelengths and reflects the red wavelength. In the second picture, red light is shown up on the tomato. The tomato is still reflecting the red wavelength and thus still looks red. But the third picture, blue light is shown up on the tomato. And since the tomato absorbs the blue wavelength of the tomato, appears to be black. Actually, this is a real life example of color wavelength. So primary and secondary color, you must know. The primary colors are red, blue, and green, and the secondary colors are yellow, cyan, and magenta. Combining pigments in painting exactly the opposite. The primary color pigments are yellow, cyan, and magenta. Secondary pigments are red, blue, and green. So light colors versus pigment, you must know for different wavelength of color, actually you get the different pigment in our real life. So the electromagnetic spectrum covers a wide range of wavelength and photon energies. Visible light ranges from 400 to 700 nanometers. About 550 nanometers, which is a yellowish green, is the wavelength to which our eyes are most responsive. Only a small portion of the electromagnetic spectrum is visible to us. The smaller the wavelength, the more energy each photons of the light has. So electromagnetic spectrum, you must know different kinds of radio waves, microwaves, infrared waves, ultraviolet waves, and X-ray, gamma rays, etc. So parallax and depth perception, you must know about this. This is also real life example of light. So first of all, we'll discuss now wave optics. Wave optics. Actually, the particle nature of light was the basis for ray geometric optics. The particle nature of light discussed in wave optics, and the wave nature of light is needed to explain various phenomena such as interference, diffraction, polarization, etc. So actually, wave optics, the wave nature of light is needed to explain various phenomena such as diffraction, interference, and polarization. So diffraction, in your real life, we get this diffraction is green shaded and interference yellow colored and polarization is like this. The particle nature of light was the basis of ray or geometric optics. So there we must know nature of light is actually two types. One is wave nature and other is particle nature. So we have to remember about these two part. So the light nature, actually wave nature, electromagnetic wave, and particle nature, bundle of energy called photons. You must know about this. And the first separate theories of ether, wave, or particle nature, corpuscular theory of Newton, 1670, light corpusculars have mass and travel at extremely high speed of straight lines. And other Huygens in 1680 give this theory, wavelets, each point on a wavefront acts as a source for the next wavefront. So why was it difficult to prove the wave part of the nature of light? Actually, proof of wave nature, Thomas Young double slit experiment, thin film interference pattern, and Poisson a group spot in 1820, and diffraction fringes seen within the around a small obstacle or through a narrow opening. So proof of particle nature of the photon photoelectric effect, you must know about in our previous lecture, we have discussed about this. This is the great contribution of Einstein, who have got a Nobel Prize in 1921. So Albert Einstein in 1905 give this light energy is quantized and photon is quantum or packet of energy. So Hertz first observed the photoelectric effect in 1887. Einstein explained it in 1905 and won the Nobel Prize for this. So Thomas Young double slit interference measured the wavelength of light. Now, first of all, what is the wave interference? So interference and the wave nature of light. This is very important part, interference of light. So owls such as this long-eared owl have eyes that can distinguish between two distant objects that are close together. This ability is related in part to the large pupils of the eyes and the wave nature of light, as this chapter discussed. So actually, the principle of linear superposition, concept of at a glance, the nature of electromagnetic wave, and the principle of linear superposition, and interference phenomena, double slit interference, thin film interference, and Michelson interferometer. The beautiful iridescent blue color of the wings of this butterfly are due to the thin film interference of light. And constructive interference, this is the example of constructive interference. So first of all, what is interference? Now, first of all, what is interference? Interference of light. Actually, objectives, you are here and you need to be there. What needs to be happen to go from here to there? Actually, this is the objectives in this part for interference. How light waves create bright and dark brightness and requirements for interference to occur. Now, light has properties similar to sound waves. Its waves properties will help you understand its interaction and object close to its own wavelength. Now, light waves. Actually, interference of light waves occurs when two or more waves meet. Actually, there are to get interference of light, we must have more than two waves to meet. In constructive interference, the wave can either match crest or trough and add together to make a bigger wave. So interference of light, in destructive interference, the wave will face the crest of one will meet the trough of the other part and will cancel each other out partially or completely. So Thomas Young was the first man to describe the properties of interference of light. So light, because of its wave properties, will have constructive and destructive interference. He sent sunlight through two narrow slits and recorded an interference pattern on a screen behind the two slits. Double slit experiment, which is given by him. The double slit experiment shows how light waves interfere with each other. There is a pattern of bright and dark fringes on the screen. And double slit experiment, the bright fringes are areas where the light travels the same distance to the screen and creates constructive interference. The dark fringes are areas where the crest of one wave matches up with the top of the other, thus creating destructive interference. So requirements for interference, in order for an interference pattern to be stable, the wave must be emitted from a single consistent wavelength or frequency, must maintain a constant phase relationship with each other. So So there are two sources. One is coherent sources. Two waves are said to be coherent if they emit same frequency or wavelength and are the phase or constant phase difference. Conditions for obtaining coherent source. Coherent sources are obtained from a single source. The source must emit monochromic light. The path interference between two sources must be very small. Actually, sunlight, many different colors, and lead one color chromatic and waves not in phase. So this is actually non-coherent. And laser light, one color monochromic and the wave phase. This is the coherent. Okay. So why can't two sources behaves as coherent sources? Two different sources can never produce waves of same phase because each source of light contains infinite number of atoms and the wave which are emitted by them will not be in the phase. The atoms, after absorbing energies, go to excited states and emit radiations when fall back to the ground state. So now we are talking about the interference. What is interference? The phenomenon of distribution of energy due to superposition of light waves from two coherent sources is called interference. This is the definition of interference. So there are two types of interference. One is constructive interference and another is destructive. In constructive interference, the amplitudes of the resultant wave is greater than that of the either individual wave. That means the sum of two amplitudes of waves will be greater than the individuals. So now distributive destructive interference. In destructive interference, the amplitudes of the resultant wave is less than that of the either individual waves. Now superposition of wave front. This is the geometrical interpretation of um, superposition waves. This is the actually constructive interference, geometrical interpretation of constructive interference. With respect to time t, the wave, and in phase, we get this one. Okay, the amplitudes will be 1. Similarly for destructive one, we get this one. Okay, that means starting from high amplitudes, but in constructive also this, and in phase we get this one. So the sum of these two wave, that means we get this one. This is the superposition of two waves and sum of these two waves. So we get this total waves, which is called constructive interference. Now destructive, this is the with respect to time, out of phase 180 degrees. You have to remember that, out of degrees. And this, after combining, we get this one. This is why wave phase destroy. So losses. This is why it is called destructive interference. So superposition, actually constructive. First one is constructive, second one is destructive, and number 3 is neither. This is different. So interference trigger need to, this is the first condition, need two or more waves, must have same frequency and must be coherent. Coherent means what? Wave must have definite phase relations. So this is the interference requirements. Now interference for sound, for example, a pair of speaker driven in phase producing a tone of a single frequency f and wavelength lambda. I'm just tan of 2 away, L2 minus L1 equals to lambda by 2, and I hear no sound at all. Actually, but the won't work for light can't get coherent sources. So interference for light can't produce coherent light from separate sources. 10 to the power 14 hertz. Need two wave from single source taking two different paths, two slits, reflection and diffraction. So this is the today's lecture, and in next one we also discuss this about. So so now we'll discuss the Young double slit experiment. Thomas Young first demonstrated the interference in light wave from two sources in 1801. The narrow slits S1 and S2 acts as source of waves. The waves emerging from the slits originating from the same wave front and therefore are always in phase. So resulting the interference pattern, the light from the two slits from a visible pattern on a screen, and pattern consists of a series of bright and dark parallel bands called fringes. Constructive interference occurs where the bright fringe occur, and destructive interference results in dark fringes. Actually, this is the source, yellow, suppose sunlight coming from this source, and this is the slit, single slit, but this is the double slit. Okay. So this is the S1 and S2, and after different phase we get this viewing screen. Okay, maximum, this is the minimum, and this is the maximum. That means it is the constructive interference, and this is the destructive. Constructive, destructive, constructive, destructive, constructive, destructive, constructive, destructive. So interference pattern on screen we get this. So actually from source, the double slit distance S1 and S2 distance D, and the midpoint is Q. So if we measure, this is the U is the OQ is the parallel line, and from the S2, this is the R2 ray, and S1, from S1 R1 rays coming and meeting at a point P. So so we get actually this triangle theta, and this is the triangle theta S1 and S2 distance D, and theta, this is the R1 rays and R2 rays from. So their difference R2 minus R1 will be D sin theta. Okay, sin theta equals to what? Sin theta perpendicular by hypotenuse. This is why we get this one. Now del is the del equals to R2 minus R1 equals to d sin theta. Remember that d, distance between slits, more and more greater than wavelength, and capital L also more and more greater than the distance between two slits. The L is the actually distance between two slits and screen. So from this, we can write sin theta is approximately equal to tan theta, because theta is very, very small. So for this, you can write sin theta is approximately tan theta. So del equals to can be written as del, this R2 minus R1 is equals to del. This is why del equals to d sin theta, and d sin theta equals to m lambda. So for this equation, we get constructive interference, and del equals to d sin theta, and we get destructive interference for m plus half lambda. So y equals to L tan theta, amplitudes L equals to L tan theta, then is approximately equal to L sin theta. This why for bright, that means constructive interference, we get lambda L by d m, and for dark destructive, we get lambda L divided by d m plus half. This is one. Okay, this and m lambda will be for constructive. So from the double slits experiment of Young, we get these two equation for both constructive interference and destructive interference. So fringe width, the expression for fringe width will be beta equals to lambda L by D, fringe width, where lambda is the wavelength. You have to remember this about this equation. Fringe width beta equals to lambda L by D. L is the actually distance between distance between slits and the viewing screen. So and D is the distance of what? D is the distance of uh, double slit S1 and S2. Okay, so from this we get this equation, and mathematical problem can become from using this equation. Now sustained interference, the interference pattern in which dark and bright fringes or positions are fixed on the screen is known as sustained interference. Conditions for sustained interference, there are three conditions. The source must be monochromatic, the two sources must be coherent, the two waves must travel with the same velocity. Actually, we must know about coherent interference, you must know. So this is the most important definition, coherent. So after this one, we can discuss about now. We'll discuss about the Huygens principle. Huygens assumed that light is a form of wave motion rather than a stream of particles. Huygens principle is a geometric construction for determining the position of a new wave at some point based on the knowledge of the wave front of that protect it. All points on a given wavefront are taken as a point sources for the production of a spherical secondary wave called wavelets, which propagate in the forward direction with the speed of characteristics of wave in that medium. After some time has elapsed, the new position of the wave front in the surface tangent to the wavelets. So as you might expect, the historic idea of the Huygens can be fully justified through various derivations associated with the Maxwell's equations. So Huygens construction for a plane wave like this at time t equals to 0, the wave front indicated by the plane A. Okay, the point are representative sources for the wavelets. After the wavelets have the moved a distance c dt, actually velocity multiplied time distance. So a new plate BB also can be drawn to tangent to the wavelengths. This is one. This is the tangent. Okay, three tangents. So this is the distance C represented by CDT and old wavelength, and this is the new wavelength after phase. So Huygens construction for a spherical wave, the inner arc represents part of the spherical wave. The point are representative points where wavelets are propagated. The new wavefront is tangent at each point on the wavelets. So Huygens construction for reflection, this is the actually another important properties of light of reflection, incident rays, and angles will be theta I, and this is the angle theta R. Okay. So Huygens principle explains diffraction actually. Okay. This is the source, and for different tangent, we get the source at point. Okay. So applying Huygens principle to two slits as one slits and other is as two slits, there is coming and screens form. So wave interference is the constructive and this is the destructive. You must know about this. So this is the double slit experiment. We have discussed about this one. So young double slits rays for double slit S1 and S2, and shadow and brightness spot will be for constructive interference, and shadow will be for destructive. So young double slits or Huygens recalls Huygens principle. Every point on a waveform front acts as a source of tiny wavelets that move forward. Okay, for double slits, and constructive and destructive for dark. So brightness and dark spot on a screen will be given. Now, consider two rays traveling at an angle theta, one coming from S1 source and another source S2. First slit and this is the second slit. So bottom ray travels at a further twice lambda in this case. Key interference. So Young's double slit quantitative, consider two rays, one is coming from R1, another is R2. And we have discussed about this in our previous slide. So we get the constructive d sin theta equals to m lambda and destructive d sin theta equals to m plus 1 by 2 lambda. So y equals to amplitudes equals to m lambda L by d and m plus 1. Just from this two, we get this one. So we can use increase, same, decreases. Okay, we can use same experiment. So Young's double slit experiment is very important for you. Some real life example of interference in field. Interference effects are commonly observed in thin films. Examples: oil on water and soap bubbles. The interference is due to the interaction of the waves reflected from both surfaces of the film. So facts to remember: the electromagnetic wave is traveling from a medium of index of refraction N1 towards the medium of the another index N2 undergoes a 180-degree phase change in reflection where N2 greater than N1. So there is no phase changes in the reflected wave if N2 greater than N1. The wavelength of light lambda n is a medium with the index n, then lambda n equals to lambda by n, shorter, where lambda is the wavelength of light in vacuum. So ray, this is another interference in film, thin film 3, and this is 1, film 4, 5. So finally we get this. So Now we'll start the diffraction of light. What's the diffraction of light? In this part, we'll discuss actually describe how light waves bend around obstacle and produce bright and dark fringes. Describe how diffraction determines an optical instrument's ability to resolve images. So in this part, we'll discuss this one. And key term, diffraction. What is the diffraction? A change in light wave direction as they pass from one medium to another. Aperture, a small slit in which light travels. Minima, the dark regions of the diffraction pattern. Prima maxima, a bright central region of the diffraction pattern. So what is diffraction? Diffraction is when light passes through an object because of the slits or holes in it, causing it to produce a light on other side of that object. So there are many different ways to diffraction, suppose colors, light, sound, water, etc. So in real life, the diffraction we can define as when waves encounter obstacles, the bending of waves around the edges of an obstacle is called diffraction. So in our real life, we can define this as a diffraction. So here's the real life example of diffraction. Uh, Here we have a source of emitting wave having planned wave fronts. As the wave fronts pass through the slit AB, they are diffracted and are able to reach even those regions. So AB means this one, this slits, single slit. So one more thing to be noted that here is that the shape of the wave fronts changes as they pass through the slits. The reason for this bending can be explained with the help of Huygens principle. So diffraction by single slit and its pattern. This is the example one. So what is the actually Huygens principle? Each particle lying on any wavefront acts as an independent secondary source and emits from itself secondary spherical wave. After a very small time interval, the surface tangential to all these spherical wavelets give the position and shape of the new wavefronts. We have discussed about this one in our previous slides. So there are two types of diffraction. One is Fresnel diffraction, and another one is Fraunhofer diffraction. So this is the mm, example of Fresnel diffraction, and second one is Fraunhofer diffraction. Now, what is the Fresnel diffraction? When the distance between the slit AB and source of light as well as between slits AB and the screen is finite, the diffraction is called a Fresnel. Fresnel diffraction of the wave are either um, spherical or cylindrical. Another is Fraunhofer diffraction. If light incident on slit AB is coming from infinite distance, the distance between obstacle A and the screen C is infinite. The diffraction is called Fraunhofer diffraction. This is very important definition for you. One is Fresnel, another is Fraunhofer diffraction. Fraunhofer diffraction is the incident waves, mm, waves, waves plane wavefronts. So this is the actually difference between Fraunhofer and Fresnel diffraction. Diffraction phenomena can be classified either as these two. So the observable difference, Fresnel diffraction, the viewing screen and the aperture are located close together, and the image of the aperture is clearly recognizable, and despite slight fringes around its periphery. As the separation between the screen and the aperture increases, the image of the aperture becomes increasingly more structured. Fringes become more prominent. So on the other hand, from Hoffer diffraction, the viewing screen and the aperture are separated by a large distance. Remember it, this is the small distance, another reason is large distance. The projected pattern bears little or no resemblance to the aperture. As the separation increases, the size of the pattern changes, but not in the shape. So here's the example of aperture array types A, and B2A is actually Fresenal diffraction pattern, and Fraunhofer diffraction only I. Okay, I is the example of Fraunhofer diffraction. So Fraunhofer and Fresnel diffraction, consider the following setup: the epoch screen summation containing a single small aperture, sum of contains single small aperture. The aperture is illuminated by the plane waves from a very distant source as the plane's observation, and del is the screen is the um, sigma is the screen parallel to the located very close to summation. So the wavelength wavefronts emerge from the aperture also play a role in determining the type of diffraction which occurs. So if both are planar, the extent and the aperture Fraunhofer diffraction, and this is the phase different from each source at point P on the screen, is due to differences in the path uh, traversed. The path difference can then be described by a linear function of the two aperture variables. The curvature of the waves are not negligible, which is implies to Fresnel diffraction. So when S is nearby the aperture, the strength and the electric field to each point in the aperture will be different. The same consideration, differences in the field strength, applies to the emergence rays directed to the observation screen. So Fraunhofer diffraction, this is the single slit. Consider the figure below. Observation point is very far from the coherent line sources. And this one, the field point P, due to the differential segment of the sources by dy is this t equals to L by R sine omega t minus kr. This is the actual angle uh, differential equation. So as this point, the expression above is very sensitive to R, where it can be expanded to the equation this R equals to R minus y sin theta y square. The dropping the third term, actually there are three term leaves us to the Fraunhofer condition where the distance R is linear to in y. So then we get a linear equation after dropping this part. So the distance to the point of observation and the phase can be written as linear function of the aperture variable. So integrating for differential segments of the coherent line source, we get the equation like this. Now, so the irradiance at point P, we get I theta equals to U square upon capital T. So if y equals to 0 at the observation on the screen, theta can be found 0, and this ratio will be 1, and I theta equals to will be this. So taking into consideration of the condition, the irradiance we written as like this. So there are symmetry about the y-axis, and the expression is correct for theta measured by an plane containing that axis. So this is the equation we got from the after calculation. And remember that capital T is more and more greater than lambda wavelength. The irradiance drops rapidly as theta derives from 0. Now, the physical slit is different from that of a coherent line source. A slit can have a width of several hundred lambda and length of a few centimeters. So this is the equation we got after calculation. And this is the physical graph of single slit aperture. This is the actually rectangular aperture, square aperture left, and right one is rectangular aperture. So the intensity of pattern concentrated principally in two directions coinciding with the sides of the aperture. So resolving power with a rectangular aperture from different source S1 and S2, angle between is alpha. So this is the reflex angle. So we get in different interference, actually destructive and instructive. So for this situation, we get theta equals to 2 lambda by b, and angular separation lambda of the central maxima is equal to the angular separation of the source. So this is the calculation. Uh, Rayleigh's criterion. Okay, circular aperture. The diagram shows the diffraction pattern formed by the plane waves going past a circular aperture. It consists of a bright ring, arrest is surrounded by a number of fainter rings. The rings shaded gradually fall off to the edges, being separated by circle of zero intensity. The intensity distributed is very much the same as that which would be the obtained with the single slit pattern, rotated about the center of an axis perpendicular to the central maximum. This is the Rayleigh of resolution limit. Two stars well separated left and two stars Rayleigh of limit right one. So it was shown that for a rectangular aperture, the angular separation is given by m lambda by b, where m is the whole number of starting from unity. Similar, um, the a similar formula can be stated with a circular aperture, but in this case, we cannot, M are not integers. Extending Rayleigh criterion for the resolution of diffraction patterns to the circular aperture. The patterns are said to be resolved when the central maximum of one falls on the dark rings of the other. The minimum angles of resolution is therefore this. So it is the aperture diameter. You must know about this one. Now double slits setup is the same as that of the single slit, but replace the opaque screen with one that of. So this is the incident plane wave, double slit, and double slit diffraction. Single slit envelope, this is the envelope created for different interference. So the two slits of width B, what's the formation? Have a center to a separation of A. Each aperture by itself would produce the same single slit diffraction on the viewing screen. So the two wave are coherent. The secondary wavelets will be coherent as well. The contribution from the two slits would be overlap interference occurs. The result is therefore then a rapidly varying double slits interference fringes moduled by a single slit diffraction pattern. This is the double slit and this is the single slit. So the total contribution to the electric field at an arbitrary point P on the reviewing screen according to Fraunhofer approximation can be shown as like this equation. And B width of slit, alpha is the K sin theta by 2 and beta is the K is sin theta by 2. So irradiance is I theta equals to, in that case, we get this. And this cos square interference term, and this is the sine term, diffraction term. So there are two types of term, where theta equals to 0 and both alpha equals to beta. If theta equals to 0, then we get alpha equals to beta equals to 0. And I0 equals to what will be 4 I naught. This whole become only 1. Okay. So if the slits are finite in width but very narrow, the diffraction pattern from the either slit will inform over a broad central region and bands resembling the idealized Young's fringes will appear within that region. So recall the diffraction pattern has minima minima at beta equals to plus minus pi plus minus twice pi plus minus 3 pi dot dot, that cause of the interference pattern to be 0 as well. Recall that beta equals to kb sin theta by 2 and minima occurs will be b sin theta by m lambda, where m is the 1, 2, 3. The interference term goes to 0 when alpha equals to right angle, okay, odd right angle, odd right angle. That means pi by 2, 3 pi by 2, 5 pi by 2, where alpha equals to k by 2 sin k sin theta by 2. Minima occurs when s sin theta equals to this angle. So n equals to 0, 1, 2. The exact position of the maxima are not given by any single relation, but by their approximation positions. Neglecting the sign term, we get s sin theta equals to n lambda, and the maxima position we get. So consider a particular situation where an interference maximum and diffraction minimum may coincide at the same angle below theta. So in the case no light is available at that precise position, the interference process is suspended at that spot. There exists a missing order like this, half fringe. This will be half fringe, and missing order will be this one. So multislits or diffraction grating. What will be the diffraction grating? Consider the case of n long parallel narrow slits, each with width b and the center to center separation a. The total optical disturbance at a point on the viewing screen can be shown with the equation this. The total flux intensity distribution will be this. Where I notice the flux density at theta equals to 0 direction, we get principle of maxima occurs alpha equals to 0. That means um, even right angle. So equivalently when s n theta equals to lambda for n equals to 0 plus minus 1 plus minus 2 dot dot. This is a general expression applicable to all values of capital N where n is must be greater or equal to 2. The radiance has a value of 0 when alpha equals to divided by capital N with the same angle, okay? So or equivalent, we get s sin theta n equals to n lambda n plus 1 into lambda by n. So between each pair of maxima, there will be a secondary maxima. So 3 slits diffraction, and this is the 5 slit diffraction. The number of secondary maxima that exist between a pair of maxima is n minus 2. In some cases, secondary maxima cannot be observed by the naked eyes, that means open eyes, as its irradiance is very low. The intensity of the maxima is the ratio of the square of the number of slits. So there are many types of Fresnel diffraction. Another one is actually Fraunhofer diffraction. You must know about this. So X-ray diffraction, another one. X-ray have the wavelength complicable to atomic sizes and spacing about 10 to the power minus 10 meter. So crystals and molecules reflect X-ray in specific patterns depending on their sources. So interaction of X-rays with atoms, okay, involves the electrons primarily. Now Bragg diffraction, this is the geometrical interpretation of Bragg diffraction. So Bragg diffraction law, W is Bragg's and W.L. Bragg's in 1923, who got Nobel Prize in 1915. Conditions for constructive interference, 2D sin theta equals to n lambda. Diffraction from different sets of planes in the crystal gives a picture of the overall structure. So single slit diffraction, we have seen about how we can get an interference pattern when there are 2 slits. We'll also get the interference pattern with a single slit provided its size and approximately lambda, either too small or not too large. So this is the experiment, same experiment we have discussed in our previous one. So this is actually single slit diffraction. So diffraction, the central maximum We get a capital L is the distance. It is the distance between two slits, and in this case, central maximum. We get, and the central maximum will be also the fringes. Figure 1 and figure 2. Here the two pattern. We'll see, notice figure 2, that is there is several bright spots and dark areas in between. First order bright fringes. So diffraction for order M, we use the letter M to represent the order of the fringes from the bright central. Actually, if M equals to 2, the second order bright fringes, if M equals to 1 first order and central maximum, this is the central maximum, and first order bright fringes M equals to 1, and this is the second order bright fringes. So it is important to understand that we see these bright fringes as the result of constructive interference, which is discussed in our previous slides. So bright fringes, the reason you see additional bright fringes is because we have constructively built. Now path difference, you must know the path difference, first wave, and this is the second wave. So one wavelength we get lambda. So the extra distance, the path difference and the order of a fringes help form a pattern. This is the actually path difference equals to m lambda. You have to remember that, which is the constructive, which is due to constructive interference. We get this one. Path difference equals to m lambda. So dark fringes, we see that definitely decrease the infinite between intensity between the bright fringes. In pattern, we visible notice the dark regions. These are areas where destructive interference has occurred. This is why dark fringes or minima occurs. So for dark fringes, we get the first for different M, order M, we get this one. And this is important to understand that we see these dark fringes as a result of destructive interference. And this is the physical phenomena for dark fringes. And path difference, 1/2 of a wavelength, that means 0.5 lambda. This is called extra distance path difference. The path difference, the order of a fringe help form of another pattern. So for the dark interference, dark fringes, we get the path difference m plus 1, m plus half into lambda. And this is due to destructive interference. Now path difference summary, for constructive interference or maximum, use path difference is m lambda, and for just destructive interference, minimum is m plus half into lambda. So you must know about the Young experiment for different path difference. We have discussed in our previous lecture. Okay, this is the example. A viewing screen is separated from a double slit source by 1.2 meter. The distance between the two slits is 0.030 millimeter. The second order bright fringes m equals to 2 is 4.5 centimeter from the central maximum. Determine the wavelength of light. Okay, actually given capital L equals to 1.2. Distance between screen and double slits. And this is the distance between two slits, 3.0 into 10 to the power minus 5. Okay, converting millimeter to meter. So order is m equals to 2 and y equals to amplitudes equals to what? 0.045 meter. That means 4.5 meter centimeter. So you have to convert the meters. So bright equals to constructive. What will be the lambda? Okay. Now we must know theta equals to tan inverse y by L. Tan means what? Perpendicular by base. This is why tan theta equals to y by L and theta equals to tan inverse y by L. Just putting the values, we get 2.15 degrees. Now d sin theta equals to m lambda. We get easily lambda equals to this one. 5 point. Now second example, another example, you can solve the lambda equal to given wavelength of 4.550 10 to the minus 9 meter, L equals to 1.80 meter, and amplitude y equals to 0.002 meter. Theta equals to what? And distance equals to what? So theta equals to same, using same formula we get 0.67 degree, and this is actually destructive for dark fringes. This is why you have to use d sin theta equals to m plus half lambda. In our previous lecture, bright fringes. This is why only m lambda. Okay, so just putting the value, we get d values. Okay, so d values equals to this one 0.000192 meter, and d equals to meter by line. So d inverse equals to 5197.2 lines per meter. Okay, now we'll discuss another part, neutron rings. Another method for reviewing interference is to place a plano convex lens on the top of flat glass surface. The air film between the glass surface varies in thickness from 0 at the point of contact to some thickness T. Actually, this is the thickness T, and this is the glass surface. This is the actually source rays coming here, and this is the tangent, and this is the point, an observer viewing this one. So neutron rings is actually another method for reviewing interference, is to place a plano convex lens on the top of a flat glass surface. So just like this, and the air film between the glass surface varies in thickness from 0 at the point contact to the some thickness T. A pattern of light and dark rings, Newton's ring, is observed. This is called the Newton's ring. So Newton rings can be used to test the optical lens. You must remember that why we need Newton's ring. Newton's ring can be used to test optical lenses. So actually, what will be the Newton's ring? You must know about this and the thickness. So a pattern of light and dark rings is observed. The rings are called Newton's ring. What is the pattern of light and dark rings is observed? These rings are called Newton's ring. The particle model of light could not explain the origin of this ring. Newton's ring can be used to test optical lenses. Actually, there are experiments to observe the Newton's ring. To study the information of Newton's rings in the air field between plano-convex lens of a glass plate using nearly chromatic light from a sodium source, and hence to determine the radius of curvature and plano-convex lens. This is the theory, and apparatus needed this, and this is the theory experiment, and Newton's ring is observed. So this is the theory for establishing Newton's ring. The bright fringes, you must know, 2 mu t equals to n plus half lambda, and the dark fringes for this. So for both interference, this due to constructive interference, and this for destructive interference. So for nth bright or dark, we also have d square n and dn square by 4 plus or minus t whole square by r from this geometry used to determine the thickness of the air film. So from here we can write, we get the radius r equals to d square n plus 1 minus dm square. And this is the procedure and observation we have to collect from the experiment and calculation, and estimate error we can find this one, and this is the discussion. Okay, question arised. So Now, in the same experiment, we can discuss in another form. The basic theory will be this. Okay, same theory, dm square equals to 4 r m lambda from both constructive and destructive interference. So set up the procedure, this one, and this one is the precaution. Okay. So similarly, for the same experiment to determine the wavelength of sodium light by Newton's ring, just using lambda equals to dm n square m minus dn square n for mr. This is the theory, and this is the experiment theory. So we can use different procedure. Okay, this is the observation table to determine the Newton ring R. Okay, theoretical error will be like this. So now another part, polarization of light. In this part, we can polarization of light definition, Drest angle, degrees of polarization, optical rotation, polarization by reflection, polarization by refraction, and Dichroism and birefringings. So what is polarization? Separating of light waves with electric field vectors oriented only in a single diffraction is called polarization of light. Or this is a process in which light and other radiations are restricted to vibrate in a single direction only, and therefore the electric or magnetic field of the wave is unsymmetrical. So Malus law, when completely plane polarized light is incident on the analyzer, the intensity I of the light transmitted by the analyzer is directly proportional to the square of the cosine of angle between the transmission axis of the analyzer and polarizer. So in that case, intensity I is proportional to cos square pi. Polarizer axis, this is the polarizer axis, and is the this is es sin theta, and this is es cos theta along base and analyzer axis. So polarization is a property of waves that can oscillate with more than one orientation. Electromagnetic waves such as light exhibit polarization, as do some other types of waves such as gravitational waves. Sound waves in a gas or liquid do not exhibit polarization, since the oscillation is always in the direction of the wave travels. So light as a electromagnetic wave, you must know, this is the figure out of magnetic field and electric field combinedly form electromagnetic wave. So what is electromagnetic wave? You must know light is electromagnetic wave. It consists of vibrations of electric field and magnetic field. The electric field and magnetic field are perpendicular to each other and in phase. Electromagnetic wave is a transverse wave. The speed of electromagnetic wave is equal to the speed of light, 3 into 10 to the power 8 meter per second. Electric field vector, this one is electric field vector. Electric field is this, and magnetic field one will be this one. So polarized light, what will be the polarized light? Vibrations lie on one single plane only. This is the polarized, okay? And this is unpolarized. Unpolarized light was superposition of many beams in the same direction and propagation, but each with random polarization. So method of polarization light, there are several methods to polarize light. It is possible to transform unpolarized light into polarized light. Polarized light waves are light waves in which the vibrations occurs in a single plane. The process of transforming Polarized light into polarized light is known as polarization. There are variety of method of polarizing light. The four methods are here. First one is polarization by transmission, polarization by reflection, polarization by refraction, and polarization by scattering. Okay, there are four types. So polarized by transmission like this, the packet friends analogy, and this is also and polarization by reflection like this, and light is coming who are unpolarized, and incident. After incident, the refraction. Okay, refraction will be reflected light will be polarized. Polarization by refraction, polarization by reflection like this. The two uh, refracted rays passing through the Iceland spar crystal are polarized with perpendicular orientations. Polarization by scattering. When light strikes the atom of materials, it will often set the electrons of those atoms into vibration. The vibrating electrons then produce their own electromagnetic wave that is radiated outward in all directions. These vibrating electrons produce another electromagnetic wave. This scattering light is partially polarized. So a polarizing materials will only allow the passage of that component of an electric field parallel to the polarization direction of the material. I equals to I naught cos square Q. So this is the I naught initial intensity of light coming and polarized at this point, vertically polarized light, and this is the polarizer. Then after we get polarized, this one I naught cos square theta, propagation direction. And this is the direction of polarizer. Okay. Now polarization in everyday situation. This photograph should be the compared with the one above. In this photo, the reflected glare that was seen on the water surface previous photos has been removed by the use of Polaroid filter. It is much easier to see the sidewalk below the water surface. So we have seen, this is our real life example of polarization. We can see the picture of sky inside the street with water. Okay. So this photograph should be the compared with the one above. The reflected glare seen on the glass panels of the lab cabinet has been removed by the use of Polaroid filter. It is much easier to see what is present inside the lab cabinets. This set of two photos provides another example of how Polaroid filter can block the annoying glare that is caused when light becomes polarized upon reflection. Okay. So action of Polaroid sunglass, light reflected from the surface like a flat road or smooth water is generally horizontally polarized. This horizontally polarized light is blocked by the vertical oriented polarizers in the lenses. So vertically polarized light from objects, the unwanted glasses are usually horizontally polarized light. Okay, this is the example, real life example of Polaroid sunglasses. Now, stress analysis. Polarized light is often used in the stress analysis of modeled plastics. Polarized light passing through the modeled plastics will reveal stress mark and stress pattern that would not otherwise be apparent to the naked eye. Or that means open eye with our natural eye. So the plane of polarization of polarized light is rotated by these modeled plastics at any location. There the plastic is stressed. The amount of rotation depends upon the wavelength of light. White light consists of various wavelengths, each associated with a distinct color. Using a Polaroid filter and rotating it with reveal stress pattern in various color at various angles of rotation. So this is another example of stress analysis. So polarization in 3D movie we also used in our real life. Um, so the polarization is often implemented in the production and viewing 3D films. When watching a 3D movie, there are actually two images being projected onto the screen once. The two images are filmed with two separated cameras from two slightly offset locations. These two images are projected onto the screen through Polaroid filters. The molecules of one of the filters is aligned vertically and the other is aligned horizontally. The audience is given 3D glasses that have one lens aligned horizontally and other aligned vertically. Thus, one eye sees one image and other eye sees the other images. The brain receives both signals and receives depth on a flat screen. This is another example of polarization in our real life. So 7-segment LCD, liquid crystal display. This is the 7 segment. Actually, there are 1, 2, 3, 4, 5, 6, 7. Okay. First one is positive electrodes, then liquid crystal sandwich. Okay, negative electrodes and polarizers. Okay, then display. So aerial. Okay, in aerial transmitting aerials, in a vertical transmitting aerial, but vertical electron oscillation resulting in a vertical polarized radio wave. So maximum electrons oscillation in the receiving aerial is achieving and the aerial is aligning to the parallel to the wave's electric field. So the sky is blue. Why? The tiny particle in the atmosphere, dust, clumps of air, molecules, microscopic water droplets, are better at scattering shorter wavelength blue light than the longer wavelength red light. As sunlight passes through the atmosphere, the scattered blue light gives the atmosphere an overall blue glow. So this is another example of polarization. The sunset is red because the sunrise and sunset, sunlight enters our atmosphere at a shallow angle and travels a long distance before reaching our eyes. During these long passes, most of the blue light is scattered away and virtually all that we see coming to us from the sun is its red and orange wavelength. This is why we see the sunset like that. So this is the real life examples of polarization, and this is important for you. Now, the polarization of light, Brewster's angle. The polarization angle or Brewster's angle. David Brewster, in 1781 to 1868, his lifetime, the inventor of kaleidoscope, was the first one who discovered that the reflected light from a plane polished surface becomes plane polarized if the reflected and refracted rays are making an angle 90 degree between them, or the sum of the incidence and refracted angle be 90 degree. Brewster's angle, also known as the polarization angle, is an angle of the incident at which light with a particular polarization is perfectly transmitted through a transparent dielectric surface with no reflections. So this is the actually David Brewster's given and incident rays unpolarized and after a reflected rays polarized. Okay, so this is the incident and this is the refracted rays on second medium. Then this is the polarized. Okay, after refracted. Now the found by this is another polarization of light, degrees of polarization founded by Provoste and designs. The degree of polarization P of the transmitted rays is related to the intensities of the reflected and refracted rays, can be calculated by the following formula with refractive index n of the slab staked m times P equals to IP minus IS divided by IP plus IS equals to m divided by m minus 1 twice n square divided by n square minus 1. A tube containing a number of piles of plate oriented at Brewster's angles called polariscope. In this equipment, two such tubes are used and both are identical. One of them is called polarizer and other is called analyzer. One of them produces plain polarized light. If the transmitted plain polarized light from polarizer is passing through the analyzer, the light intensity can be controlled by the orientation of the tube along the wave traveling direction. So angle will be n pi, where n equals to dot dot plus minus 3 plus minus 2 plus minus 1 0. Okay, infinite. So between tubes along the tube axis produces maximum intensity of polarized light, while angle will be and times multiply with the right angle. That means n equals to dot dot plus minus 3 plus minus 2 plus minus 0 produces zero intensity of the transmitted light. So polarized light of optical rotation. What is the optical rotation? When a plane polarized light is passed through the certain crystals, they rotate the plane of polarization. Quartz and sodium chlorate crystals are typical examples, which are termed as typical active crystals. A few millimeter thickness of such crystals will rotate the plane of polarization by many degrees. Certain organic substances such as sugar and tartaric acid show optical rotation when they are in solution. This property of typically active substances can be used to determine their concentration in their solution. Polarization can be achieved in 5 ways: reflected transmission, pile of plates, dichro, uh, dichroism, uh, birefringence, scattering. By reflection. First one, by reflection, if light strikes in an interface so that there is a 90-degree angle between reflected and refracted ray, the reflected light will be linearly polarized. That is, all the light after reflection has only one electric field vector vibrating in a single plane only. The direction of polarization, the way of electric field vectors point, is parallel to the plane of interference. The special angle of incidence that produces 90-degree angle between reflected and refracted ray is called the Brewster's angle, phi p. We have discussed about this in our previous slide. A light geometry shows that phi p equals to n2 into n1. So by reflection, we get the light of a non-metallic surface results in some degrees of polarization parallel to the surface. Okay, unpolarized incident light, and after refracted, polarized reflected light becomes. So different angle, similar angle produces. That means polarized. So by refraction, another one is refraction. Polarization can also occur by refraction of light. The polarization occurs in a plane perpendicular to the surface. Iceland spar, a rather rare form of the mineral calcite unicrystal fractures incidents light of two different paths. The light is splits into two beams upon the entering the crystal. Hence, two images are seen. Both refracted light beams are polarized, one in direction parallel to the surface and other in the direction perpendicular to the surface. Okay, the two refracted rays two, because this is the three-dimensional space. Reflect passing through the Iceland spar crystal are polarized with the perpendicular orientations. So now polarization of light with dichroism. First of all, the property of definition, the property of some crystals and solutions of absorbing one of two plane polarized components of transmitted light more strongly than other. Also, it is the property of exhibit different colors by reflected or transmitted of light. It is a polarization technique due to absorption. A number of crystallic materials absorb more light in one incident plane than another. So the light beams progressing through the material become more and more polarized as they proceed. This anisotropy, the absorption, is called dichroism. There are several natural occurring dichroic materials, and the commercial materials polaroid also polarized by the selective observation. Now, materials which have different absorption and perpendicular incident planes of light are said to be dichroic. The mineral tourmaline is the best known of natural materials. Tourmaline refers to a class of boron silicates A tourmaline crystal has a unique optic axis and any electric field vectors which is perpendicular to that axis is strongly absorbed. Polarized is the trade name of the most commonly used decorative material and selectively absorbs light from one plane, typically transmitted less than 1% through the sheet of Polaroid. Now, birefringence is the optical property of material having a refractive index that depends on the polarization and propagation direction of light. These optically anisotropic materials are said to be birefringent or birefractive. The birefringence is often quantized as the maximum difference between the refractive indices exhibited by the material. Crystal with non-cubic crystal structure are often birefringent as the plastic under mechanical stress. Birefringence is responsible for the phenomenon of double refraction, whereby a ray of light, when incident upon a birefringent material in split by polarization into two rays, taking slightly different paths. So this is the example for birefringence. Polarization of light, the magnitudes of difference quantized by the birefringence is del n equals to Ne minus N naught, where N is the optical index and N naught is the refractive index ordinarily. So this is the optic axis and parallel polarization, perpendicular polarization. This one. This is the parallel and this is the perpendicular. So two indices of refraction characteristic by birefringent material. Such material from uniaxial crystal and may be characterized as positive or negative. Uniaxial crystal based on the comparison of the indices. Some birefringent material, this is the crystals, tourmaline, calcite, quartz, sodium nitrate, ice, rutile, and this is the anode and this is the anode. Now crossed polarizers. An ideal polarizer produces linearly polarized light from unpolarized light. Two ideal polarizers would eliminate all light of their transmissions direction are placed at right angle. The two sheets of Polaroid at left are crossed and placed on one overhead projector. Polaroid is not an ideal polarizer, so some light is transmitted even when the sheets are crossed. This is the unpolarized light, and after coming to this transmission orientation and linearly polarized light and another transmission orientation. So this is the end of actually polarization. In our previous lecture, we have discussed about applications of polarization. This is an important question for you. Application of polarization. We have discussed this in our real life. Okay. Okay. This is the Malus law. This is important law. The intensity of polarized beam transmitted through the second polarized sheet I equals to I naught cos square theta. I naught is the intensity of polarized wave incident on the analyzer. This is known as Malus law and applies to any two polarizing materials whose transmission axes are to an angle theta to each other. So this is important law for you. And so the physical interpretation of Malus law, the transmitted light has maximum intensity when the transmission axes are aligned with each other like this. And the transmitting light intensity diminishes when the transmission axes are at an angle 45 degree. Okay, 45 degree with each other. The intensity of light transmitted depends on the relative or orientations of the transmission axis. So the unpolarized light after transmission polarized. Okay. So I equals to I naught cos square theta. This is the Malus law. And polarization by reflection, we have discussed this one. And polarization by refraction also like this. In mathematically, we can polarization by scattering. Okay, polarization by scattering and optical activity. Certain materials are optical active and liquid crystal. A liquid crystal is a fluid substance whose molecules exhibit some orientational order as a solid crystal. Okay, if we see coming incoming light, polarizer, this is the polarizer and this is the glass. Liquid crystal here and glass, and this is also polarizer and reflecting surface. Light goes through the segment is bright. LCD liquid crystal display, light is blocked, the segment is dark. Okay, so crystal, liquid crystals, and this is the 3D movies. Okay, this is the Planck constant and given by Max Planck, which is which value 6.626 into 10 to the minus 34 joules second. And this is the coherent light. What is coherent light? Lamps, flashlights, etc. all produces light, but the light is released in many directions, and the light is very weak and diffuse. In coherent light, the wavelength and frequency of the photon emitted are the same. Okay, same. The amplitudes may be vary. Such things as lasers and holograms are composed of coherent light. This is the example of coherent light and incoherent light. So lasers, you must know about. This is also the modern use of light or optics. Laser stands for light amplification by stimulated emission of radiation. A laser is a device that creates and amplifies a narrow intense beam of coherent and non-chromatic or one wavelength light. Here's how they work. Okay, you must know about this. So holograms, you must know, as with any type of wave, light waves can interfere with one another. The interference of two or more waves will carry the whole information about all the wave. It is on the basis of that holograms work. Holograms make use of lasers and they work in the following fashion. Okay, laser coming and object beam spreader. Okay, this is the objects and beam spreader, reference beam, and this is the mirror, light wave interference, and film plate. Okay, in this way holograms work. So this is actually a description of hologram, how image forms. Luminous flux and luminous, you must know about this one. And this is the luminous versus distance, 1 meter, 2 meter, 3 meter, and 4 meter. Okay. So solid angle, you must know what is the solid angle. The sphere whose circle circumference of a circle is 2 pi r, and solid angle value equals to s equals to 4 pi r square. You must know. So luminous intensity, what is the luminous intensity? Is given by I equals to pi divided by 4 pi. Efficiency of light source, efficiency is given by pi by p, where p is the power. Okay, and phi is the flux, magnetic flux. So okay, now we will discuss some important properties of geometrical optics, review of image information, image formation. This is the object outside the twice focal length region, real inverted diminished, and this is the real inverted and same size, and real inverted and enlarged. Okay, and parallel rays, no image formed. Okay, and vertical erect and enlarged. Okay, depending on the position of objects between the focal length and twice focal length, we get virtual, erect, and enlarged image. Now, all images formed by diverging lens are erect, virtual, and diminished. Images get larger as objects approaches. So, diverging lens from focal length, any rays incident to an concave lens, we get diverging lens. Okay. So, analytical approach to imaging. Now, you get this one. And lens equation will be 1 by p, and p is the distance from the distance of objects from the center of lens, and q is also the distance of image, and f is the focal length. So magnification will be what? M equals to uh, image and length of image divided by length of object. Now, working with principles, the lens equation can easily be solved by using a reciprocal button 1 by x on most calculators, possibly sequence for finding f on linear calculations, finding f p equals to 1 by x plus q into 1 by x equals to 1 by x. So sum with reverse notation calculation might be finding f will be like this. So alternative solution, it might be useful to solve the lens equation algebraically for each of the parameter, like this 1 by p plus 1 by q equals to 1 by f. So p equals to qf divided by q minus f. And we also find f equals to qp plus divided by q plus p. And we also can find q equals to pf minus p minus. Be careful with substitution of sign numbers. Now example 3, a magnifying glass consists of a converting lens, focal length 25 centimeter. A bag is 8 millimeter long and placed 15 centimeter from the lens. What are the nature, size, and location of the image? Okay, this is the image object position, and its image will be created like this. Okay. That means if p equals to 15 centimeter and focal length, position of objects p equals to 15 and focal length 25 centimeter, then using this equation, we get the result. Position of image will be found minus 7.5 centimeter. Minus indicate that this is the outs and large. Okay. The fact that q is negative means that the image is virtual on same side of as object. We have to remember this one. Now another example, a magnifying glass consists of a converting lens, focal length 25 centimeter. A bag is 8 millimeter long and placed 15 centimeter from the lens. What is the size of the image? Actually, size will be given by this equation, and size will be given by this 20 millimeter. Okay. The fact that y dash is positive means that the image is erect and it is also larger than object. So positive means erect and larger than object. Now another example, what is the magnification of diverging lens, focal length 20 centimeter, if the object is located 35 centimeter from the center of the lens? In that case, we have to find out q, okay, then m, using these two equations. Okay, q equals to, we get minus 12.7 centimeter, and m equals to magnifying with values 0.364. Okay, so summary, a converting lens is one that refract and converts parallel light to a real focus beyond the lens. It is thicker, near, and middle. Okay, and the principal focus is denoted by the red f. The diverging lens is one that refracts, and diverges parallel light which appears to come from a virtual focus in front of the lens. This is the example. Okay. So summary of math approach. Okay, lens equation and magnifying equation is this. So this one, sign convention. Object P and image Q distance are positive and real, and image negative for virtual images. Similarly, the image of height y dash and magnification m are positive for erect negative and for inverted images. The focal length f and the radius of curvature r is positive for converging mirrors and negative for diverging mirrors. So today we have discussed about the actually two types of optics. One is geometrical optics and another is physical optics. Actually, we have concentrated on physical optics. Actually, the father of modern optics, you must know Haytham. Okay, so you must know about him. Actually, he is the father of Ibn al-Haytham. He is the father of modern optics. In his lifetime, 965 to 1040, he discovered many parts of modern optics, and he is considered as the father of modern optics. He was a great mathematician, astronomer, physicist, and Islamic golden age Islamic golden age from present day in Iraq. Okay, he's the father of modern optics, and we have to remember him. Okay. So thanks to everybody. Okay, bye for today.